Alright guys, today I'm going to go over Firestarter 1, Firestarter 2, Firestarter 3, and I'm going to go over those notes. It's going to go a little bit quicker just because a lot of this we've already talked about. So this is a picture of the board. If you cannot see this, this is a picture of the board if you're not sure where it came from. So picture of the board, we're going to use this quite a bit. So anytime, remember in 1.5 we learned about perfect squares. In 1.5 we learned about these perfect squares. We found out that if any of these blue numbers are divisible by the number in the radical, then there's work we have to do. In 1.5 we learned about conjugates. We learned about the conjugate box. We also learned about how to solve in 1.5. So we learned all that. None of those ideas can be forgotten. We have to remember all those ideas. In addition to that, we now know about I. Remember, I is cyclical, so I can never be left with an exponent because you can simplify it. I to the first is I squared is -1, I cubed is negative I to the fourth is I, and it goes on forever and ever. We learned about complex conjugates. Remember, I call them conjugate soulmates, right? When they multiply together, they make the I disappear, right? Just like we had conjugates with radicals that they multiplied together and the radical disappeared. So none of that's new. We're still going to solve just like we did in 1.5, except I is going to show up. And the other new idea we're going to talk about today is absolute value. So all that's new stuff. And then we'll go from there. All right, so today the Firestarter 1 is all about PEMDAS backwards. So remember PEMDAS backwards. That's how I get my free point. If I am lost, the first thing I do is I write PEMDAS backwards, because if I know it's a solve problem. I know it's a solve problem for two reasons. One, it says solve right here. Two, we have an equal sign with one variable. So that's the big key, is you can only do PEMDAS backwards if there's one variable, which we do have here. So all I do to figure out if I'm allowed to use PEMDAS backwards or to use PEMDAS backwards is I start from the bottom. I look for subtraction. I don't see any. I don't see any addition. I don't see any division. I don't see any multiplication. I see an exponent. How do I get rid of an exponent? Well, I use the square root on both sides. So that means I have to square root both sides. And remember, whenever we square root both sides, plus or minus shows up. It's the most common mistake. People forget to put the plus or minus. So I already know plus or minus shows up. X equals, well, the square root of 28 is our answer. Now there's two answers. It's positive square root of 28, minus square root of 28. Now remember, we cannot forget that we had to break down radicals. We cannot forget that 28 is not perfect, but to leave jail, you have to be perfect. So that's where those numbers come into play. So I look and see 28 is not on my list here. 28 is not on my list. All right. But 4 goes into 28 7 times. Now remember, to leave jail, you have to be perfect. So look, this 4 is going to leave the jail. He's going to turn into 2. This 7 is going to stay in jail forever. So my best answer is X equals plus or minus 2 radical 7. Look, I did not show up. Number 1 is basically a 1.5 problem, not a 1.6 problem, because I did not show up. Notice they're not going to look any different from the start. You're not going to know right away whether I is going to show up or I is not going to show up. That's the idea we talked a little bit about in class yesterday. So number 2, the exact same concept. I want to get my free point, so I put PEMDAS backwards. If you're not sure, like I said, this is a solve problem. This tells me you are trying to follow the steps I am outlining in class. This shows a little bit of effort. There is no subtraction in number 2. There is addition. I see z squared plus 8. How do I get rid of addition? Right, how do I get rid of addition? I use subtraction. So I minus 8 from both sides. I end up with z squared equals -4. Now, the addition's gone. There is no division. There is no multiplication. There's an exponent. That's an exponent. How do I get rid of an exponent? Well, I square root both sides. So I square root both sides, just like we did in the last problem. I end up with z equals, and remember, whenever I square root both sides, plus or minus has to show up. Now, the only difference in this section the absolute only difference in this section is that when I square root both sides, and there's a negative in the radical, the negative is allowed to leave the radical as long as it turns into I. So, although negative is not on my list of perfects, there is no negative here. Right? There is no negative there. The negative turns into I. And now I know the square root of 4. The square root of 4 is 2. So my best answer is actually z equals plus or minus. The square root of 4 is 2. You always put your number part first. But if you were I2, I wouldn't take off for that. So that's it for number 2. 3, first thing I'm going to do, like I said, if I'm lost, I'm going to put pendulums backwards. All right, I don't see any subtraction. I see addition. So how do I get rid of addition? I'm minus 31 from both sides. Now I have 2x squared equals 9 minus 31. So if you're not sure, you just grab your calculator, do 9 minus 31. If you can't do it in your head, you end up with negative 22. The addition's gone. There is no division. There's multiplication. This 2 is multiplying by x squared, so I have to get rid of multiplication by division. That's why I divide by 2 on both sides. I try to do it the same way every single time. That's why I do it this way. So we end up with x squared equals negative 11. The multiplication's gone. Now I have to see if there's an exponent. There's an exponent. I square root both sides. Remember, plus or minus is going to show up. Also remember, this negative sign is going to turn into I. So the negative inside the radical automatically turns into I. That was the one idea we talked about yesterday. It's the only new idea in this entire section. Everything else is exactly the same. And square root 11 cannot be broken down, so we're done here. So I'm still going to use pendulums backwards. I'm going to continue to use pendulums backwards. On number 4. Now remember, on number 4 it says 1 variable. I have 2 variables. But luckily, they are the same type of variable. That means I can put them together. So before I do worry about pendulums backwards, the first thing I do is I see if I can put my variables together. I subtract 2t squared from the right side because that makes it go away, which means I have to subtract 2t squared from the left side. Those are like terms. So my whole problem turns into 4t squared plus 5 equals 1. So now we do have one variable, so I am going to use pendulums backwards just like we've done before. So like I said, if you want to get your free point, just write pendulums backwards. Even if you mess everything else up, you're at least going to get a point for that. And then I look, there is no subtraction, there's addition. I minus 5 from both sides. I end up with 4t squared equals negative 4. Now, I get rid, the addition's gone. There is no division. I see multiplication. That's why I divide by 4 on both sides. Some people are going to see that 4 as being perfect and try and square root it. In some cases, that will work. But most of the time, that's not going to help you. So I always just try to follow the same steps every single time, which is why I divide. I end up with t squared equals negative 1. The m's gone. Now, how do I get rid of an exponent? I square root both sides. So t equals, remember, whenever you square root both sides, plus or minus shows up. And the square root of negative 1 is I. And that's the math reason why anytime you have a negative inside the radical here or here, that's why it comes out as I, mathematically. All right? Last one. Once again, the first thing I do on number 5 is I do pendulums backwards. And this is one of the problems I really recommend using pendulums backwards because I see a lot of mistakes here. So the first mistake I'm going to see is I'm going to see somebody do this. Don't do that. Not allowed. All right? Don't do that. All right? That's because you're using negative 5, that's multiplication, and you're getting rid of it by multiplication. That's not what I teach. All right? There are some instances where that'll work, but the main reason why that doesn't work is because of the little 2. So do not do that. The other mistake I see is somebody takes this 2 and they try to do that. Don't do that either. That's not allowed either. That's breaking. That's getting rid of an exponent by using multiplication. That's not what we do either. So don't do that. No. All right? So we're just going to follow our order of operations like we've been doing. I'm going to look at my problem. I'm going to see, do I see any subtraction? I do see subtraction, but it's actually in the parentheses, so I can't get rid of that subtraction yet. All right? So don't get tricked. The third most common mistake is somebody's going to add 3 to both sides. Do not do that. There is no addition. There's no division. There's multiplication. And I teach you to get rid of multiplication by division, which is why I divide both sides by -5 first. So I end up with n minus 3 squared equals -2. Now that subtraction is still in the parentheses, so I can't get rid of the -3 yet. There is no addition to division. There is no multiplication. Now, how do I get rid of an exponent? I've taught you to get rid of exponent by square rooting both sides. So that's what I do. I square root both sides. Remember, whenever I square root both sides, plus or minus shows up. I have n minus 3 equals plus or minus. Remember, the negative automatically turns into I. You can do it later, but I always do it as soon as I see the negative. On the next step, I always just make that I show up. So the negative is kind of like it's perfect. You have to imagine the negative sign's perfect. Remember, if you're perfect, you get to leave jail as long as you change. So negative sign leaves jail, but he has to change into I. The last thing I'm going to do is now, finally, the parentheses are gone, so I get to focus on the subtraction, so I add 3 to both sides. Now remember, the plus or minus already happened, so the 3 is addition. It cannot jump in front of the plus or minus. So that's our best answer. Now, sometimes people are going to write this as 2 different answers. This is technically 2 different answers. But I'm not going to make you write it as 2 different answers. All right? So that's it for Firestarter 1. All right. Firestarter 2, it's very simple. It's going to use this idea of distributive property, FOIL if you want to think of FOIL. And remember we talked about how I creates a cycle with exponents. So anytime I has an exponent, you have to simplify it down to no exponent. So, and that's our cycle there. We're also going to use this idea of complex conjugates for number 3. So number 1, I have I is a pizza delivery guy. He's going to distribute over to 4. He's going to go over to -8i, so I get 4i. I times -8i is minus 8i, and I times I is I squared. Now hopefully I remember that I squared is -1, and it says it right here. So I squared is actually -1. So if I replace this guy right here with -1, so if I take I squared and I were to erase it, and -1 takes his spot, well, -1 times -8 is +8. So that's why whenever we see a -1, or an I squared, we just change the number in front. It makes things much quicker. Now to write this, you always put your real part first, so 8 plus 4i. Although I would not take off if you wrote 4i plus 8. There will probably be some math teachers who do that, so be careful there. Number 2, I'm going to do distributive property. You can think of it as FOIL as well. So you can FOIL or distributive property. I like to think of it as distributive property because then it doesn't matter if it's two things in one parentheses times 2 things in another parentheses, or 3 times 3, or 3 times 5. Doesn't matter. All right. With FOIL, FOIL only works for 2 things times 2 things. But either way, the green writing is going to be the first and the outside, and the purple writing is going to be the inside and the last. I think of it as -2 as a pizza delivery guy. He goes over to -1. That gives me +2. Now -2's got to finish his job. He's going to go over to 4i, becomes minus 8i. Now 5i is a pizza delivery guy, or you're doing the inside. 5i times -1 is minus 5i. And then 5i times 4i is 20i squared. I forgot to write the plus sign. And then hopefully remember that anytime you see an I squared, you just cross it off. And instead of writing plus 20i squared, I just write minus 20, because I squared is -1. Now I put my real friends with my real friends, I get -18. I put my imaginary friends with my imaginary friends, minus 13i. And we are done. That's it. Now, I could do number 3 the exact same way I did number 2, but I'm actually going to use this shortcut because they are conjugates. Remember, conjugates have to be the exact same numbers, but they have to have different signs in the middle, which these guys do. So I'm going to use my shortcut. So all I do is I take the first number and I square it. So I take 8 and I square it. Then I find the next number without I. Look, I don't even use I. And that's it. So I do 8 squared, which is 64, plus 25. So my final answer for that one, 89. Now, if you FOILed it or use the distributive property like I did number 2, you'll get the same answer. Right? Now, the other thing we talked about in class this week was absolute value. Absolute value is distance from 0. When we over notes, I'm going to show you the complex number plane. So distance from 0, it's always positive and real, because distance can never be negative. Doesn't matter if you run forwards or backwards, you're always traveling, and it's always real. It's never imaginary. So I don't use the I. I don't even worry about the I. Actually, I don't even worry about it's much easier, honestly, if you don't even worry about the negative sign. So the absolute value, I just can use this formula. This is based off Pythagorean's theorem. We talked about it in class. So this is my A, and this is my B. So all I'm going to do is I'm going to say, and they just say Z is a fancy way to write A plus BI. So if that Z is bothering you, just don't even think of it like that. So I'm saying the absolute value of negative 3 plus 10i, remember that's what the bars mean, equals the square root sign. And A, I'm going to ignore the negative sign, so I'm just going to put 3 squared. And then I'm going to do B without the I. So it's just the square root of 3 squared plus 10 squared. 3 squared is 9, 10 squared is 100. So this whole thing is going to turn into, so the absolute value of negative 3 plus 10i equals the square root of 109, because remember 3 squared is 9 and 10 squared is 100. Now I do have to see if I can break that down using my perfect square numbers, but you can't. So it's it. That's it. Done. All right. 5, exact same concept. So I'm going to say the absolute value of 4i equals, well, this is always B. B is always with the I. There is no A. So in this case, we just put 0 squared plus 4 squared. So the absolute value of 4i equals 16, which is 4. And that should make sense. And you'll see if you can easily do the absolute value of 4i on a number line and have no problems counting it to get 4. So it works. And that's it. All right. Firestarter 3 is almost the exact same concept as Firestarter 1. So remember, PEMDA's backwards because it's a solve problem. So the first thing I do on number 1 is I put PEMDA's backwards because I want to get my free point even if I mess any things up. Then I'm going to go through and look for subtraction. I don't see any. I see addition, so the first thing I do is I minus 10 for both sides. The reason I teach it this way is so every single time, if it's a solved problem with one variable, you literally attack it the same way every single time. Now I get rid of there's no more addition, there's no division, I get rid of the multiplication. I don't care that 36 is perfect, I only care that I see multiplication on the left side. Now I have x squared equals negative 12. Now I got rid of the multiplication, now I have to get rid of an exponent, that's why I square root both sides. So I have x equals, remember whenever I square root both sides, plus or minus shows up. Remember if I see a negative inside the radical, I shows up. Also remember 12 is not perfect, but 4 goes into 12 3 times, and 4 is perfect. So 4 gets to leave jail, he turns into 2. 3 has to stay in jail forever. That's our entire problem. So I did go a little bit quicker because this is something it is very similar to what we did in Firestarter 1. So I did explain this a little bit slower in Firestarter 1. So number 2, same exact thing, PEMDA's backwards. No subtraction. There's addition, that's why I'm minus 11 for both sides. I end up with 2x squared equals minus 48. Addition's gone, no division. There's multiplication, that's why I divide by 2 on both sides. I end up with x squared equals negative 24. Get rid of the exponent, that's why I square root both sides, square root, square root. So I end up with x equals plus or minus, remember, this negative, he gets to leave jail as long as he changes into I. And then we're going to look at 24. 24 is not perfect, but 4 is perfect and goes into it 6 times. I don't care about 3 and 8 as factors because neither one of those are perfect. I don't care about 2 and 12 as factors of 24. Neither one of them are perfect. So this 4 turns into 2, and then 6 stays in jail forever. That's it for number 2. 3, exact same concept. I start with PEMDAS backwards. Now remember, PEMDAS backwards says you have to have one variable. So before I do anything, I'm going to make sure I can put my variables together. I like to do this first because then if I can't put them together, let's say that was t to the first on the right side, then I would know I'm not wasting my time trying to use PEMDAS backwards. I would maybe have to factor like we did in previous sections. So I have 4t squared minus 5 equals negative 1. Now, I see subtraction, that's why I add 5 to both sides. I end up with 4t squared equals 4. Addition's gone, no division, there is multiplication, that's why I divide by 4 on both sides. I end up with t squared equals 1. Now I got to get rid of the exponent, so I square root both sides. I end up with t equals plus or minus, and 1 is the only number that can leave jail without changing. It's got some special 1 privilege. He can leave jail without changing 1. Notice, I does not show up because there is no negative in the radical. I don't want you guys to get, I purposely did this to let you know that this problem is actually a 1.5 problem. It looks very similar to anything we've done on 1.6. So when you're doing them together, 1.5 and 1.6 at the same time, you're not going to know ahead of time whether I will or will not show up. Your radical at the end is going to tell you whether I shows up or not. All right, number 4, exact same concept, PEMDAS backwards. So, remember, there is subtraction, but it's actually in the parentheses, so I cannot get rid of that minus 2 yet. There is no addition, there is no division, there's multiplication. Remember, you get rid of multiplication by dividing. I talked a lot more about this in detail in Firestarter 1. So remember, I'm not using multiplication to get rid of multiplication. I'm using division to get rid of multiplication. And that's why I have n minus 2 squared equals negative 5. Now, I have to get rid of the exponent. How do I get rid of the exponent? I square root both sides. Don't make the common mistake of getting rid of the exponent the wrong way. So I end up with n minus 2 equals, remember, whenever I square root both sides, plus or minus shows up. This time I do see a negative in the radical, so he gets to leave jail as long as he turns into I, and 5 stays in jail forever. Now look, our parentheses are finally gone. After our exponent is gone, I can finally get rid of that subtraction by addition. So I have n equals 2 plus or minus I radical 5. And that's it. Done. I'm going to go really quick here because I already went over this in class. So, not all quadratic equations have real number solutions. In the case of x squared equals negative 3, there are no real numbers squared that equal a negative number. To overcome this problem, mathematicians, remember our friends John and Betty, create an expanded system of numbers using the imaginary number written as I. And then we talked about how I is the square root of negative 1, I squared is negative 1, I cubed, etc., etc., etc. Now, there is a property. Remember, there was some fine print. This is just math fine print. If R is a positive real number, then the square root of negative R, remember, we found out that the negative gets to leave the jail and turn into I. And then whatever's left over stays in jail. And it can be broken out if it needs to. Now, mathematicians like this idea of continuity. They like things to be able to work and continues to work. So, for example, we should have known a long time ago, we learned that if you take the square root of 3 and you square it, the check mark and the little 2 cancel each other out, and you're equal to 3. So if I were to square, oops, I wrote that wrong, the square root of negative r, like we would already know, it should turn into negative r, right? And it does. Now, what that means is that this part right here, if I were to square it, since they are equal, so they should turn into the same exact thing. Basically, they're saying if this property 1 is correct, I should be able to get negative r here. And that's what happens in number 2. And then we don't use it a lot, but it says, because property 1 is true, then we get to say this. I square root of r, and if I decide to square it by our math rules, I have I squared times r squared. Well, we know that this guy is negative 1, and this is r, so it does turn into negative r like they thought. So here's a quick example. If I have the square root of negative 3, remember, I comes out of jail, 3 stays in jail. If I were to take I square root of 3 and I were to square it, I would end up with I squared times radical 3 squared, which is in fact negative 3. The next part, see previous Firestarter if you didn't get that. The keyword is green calculator. The keyword is green calculator. All right, a complex number, so we're going to use this word. So this is a complex number. Remember, a complex number, that means that any number can be complex, whether it's real or imaginary. Written in standard form, a plus bi. So this is like generic version of any number can be written as a plus bi. That means any number is a complex number. So that means imaginary numbers are part of complex numbers. The number a is the real part of the complex number bi, and the number bi is the imaginary part. So they like to break it down into an imaginary part and a real part. If a is 0, which means if it's just an imaginary, if it's just like 4i or 7i, then we call that a pure imaginary number. Now, every complex number corresponds to a point in the complex plane. All right? And basically, the complex plane is a long time ago, if you guys remember our friends John and Betty. John and Betty said, we have a number line. Right? There's 1, there's 2, there's 3, 4, 5, 6. Just like we had in like grade school. -1, -2, -3, -4, -5. That's a number line. And zeros in the middle. Right? Now, John and Betty talked about how we need to be able to put our real numbers and our imaginary numbers together. 0 became like the most important part because 0 and 0i are the same thing. So that means I could connect my two lines at 0. So this is I, 2i, 3i, 4i, 5i, 6i, and this would be -i, -2i. That only works because 0 is the same as 0i. And now, mathematically, we have put our number line, we have made I fit on our normal number line, but it just made a different axis. So it's called a plane. Right? And it's really easy to graph it. Real parts are left and right. Left if they're negative. Right if they're positive. Imaginary are up and down. Up if they're positive. Down if they're negative. So here, I go left 4 because it's -4. I go down 1. So I go left 4, down 1. There's point A. Really easy. B, I just go right 5. Because there is no imaginary part. C, I go right 1, up 3. So C, I'm going to go right 1, up 3. And then D, I'm going to go down 2. So I go down 2. That's it. That's all plotting points on a number line. That's all it is. It's just we have 2 parts, so there's 2 axes, and it's just directions, left and right, up and down. That's it. And now the absolute value is trying to figure out how far. That's the absolute value. They want to know how long is that line from A to the origin, right? And that's what we're going to talk about next. This is like the one of the last Firestarters we did. So if you didn't figure this out yet, Firestarter 33 went over this one. And Firestarter 3 went over that one. So your notes should